Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we plant the seeds of weird and wonderful science directly into the soil of your fertile imagination. I'm Ian Woolf. On this edition, we feature a blast from Diffusion's past, digitised from audio compact cassette and recorded in the days when we were broadcasting live from the studios of 2SER as the Discovery Science Show. This episode is from the 16th of November in the year 1999, where the sound quality was variable and cassette tape changed the way voices sounded. In this episode, we investigated women in science, the Mindswitch, and quantum computing. David Blank reported news of Martian probes and exoplanets. Here's Discovery 1999.
Hi, this is Douglas Adams. I'm the author of The Hitchhiker's Guide to the Galaxy, and I'm here to urge you to listen to the National Science Program on Discovery. Your hard copy right there.
Maximum velocity.
This is Discovery, 2SER's national science show where science, arts and culture meet to educate, inform and entertain. I'm Carol Oliver. On this edition we'll look at the issues facing women in science, at machines that respond directly to human thought, and explore quantum computing. But first up, the news with David Blank.
NASA's Deep Space 2 microprobes to the South Pole of Mars have been named Amundsen and Scott in honor of the first explorers to reach the South Pole of Earth a century ago. The microprobes are due to smash into the ice of Mars on December 3rd as part of a bid to test flight advanced technology that could be used by future planetary surface microlanders. The naming of the probes was submitted to public contest, won by Paul Withers, a U.S. graduate student studying the thin upper atmosphere of Mars. Withers said that Amundsen had explored the Northwest Passage before leading the first unsuccessful expedition to Earth's South Pole in 1911. Scott succeeded a year later, and his memorial inscription also applied to the aims of Deep Space 2, to strive, to seek, to find, not to yield. Greg Henry and his colleagues at Tennessee State University have confirmed that the star HD 209458 does have a planet orbiting with a period of about 3.5 days. Previously, from the wobble in the motion of the star, the planet's mass was worked out to be about 2/3 that of Jupiter, the most massive planet in our solar system. Henry found that the star dimmed by about 2%. From the amount of dimming and its duration, the size of the planet moving in front of the star was worked out to be about 2/3 greater than that of Jupiter. From the previously known mass and its now known size, the density of this object is only 1/5 that of water. This means that if one could find a big enough lake, the planet would float. The Swedish Nobel Prize Committee have announced the winners of the 1999 Nobel Prize in Science. The award in medicine and physiology went to Dr. Gunther Blöbel of the Rockefeller Institute in the U.S. for working out how protein molecules are able to move in and out of body cells. The chemistry prize went to Ahmed Zawel at the California Institute of Technology, also in the U.S., for using laser pulses to study chemical reactions. Professor Zawel is the first Egyptian to win a Nobel Prize, and he did not become a scientist until he was 38. Two Dutchmen, Martinus Veltman and Gerardus de Hoof at the Utrecht University in the Netherlands, won the Physics Prize. They developed a mathematical framework used in particle physics, and their work is also important in the development of quantum computers, which would be much faster than the computers currently used.
You're listening to Discovery, the national science program broadcasting across Australia via ComradeSat. More than 200 female Australian scientists recently met in Melbourne for a conference on women achieving in science. Matt Whitfort spoke to Dr Michelle Smyth, president of the CSIRO section of the CPSU, who opened the conference, about the issues facing women in science today and what the future holds. He begins by asking her about the ideas behind the conference.
Well, the idea is that women enter science in numbers that are quite high, but after about 5 to 10 years, a lot of them drop out. And we were trying to find out why women find it difficult to progress in science. And the other idea is that many women are eminent in their fields, but nobody knows about them, and they're not often recognised as the experts in their fields, even though they've achieved just as greatly as men in similar fields have done.
Okay, so what were some of the findings of why women do drop out of science?
We had 10 workshops about this. I can't tell you the definitive answer to that. I think part of the problem is that women are not as aggressive as men in the political field. When they're at work, they do their jobs and they don't enter into the politics of the workplace.
Yep.
And it seems necessary to do this to get on into better positions and to become better known.
So would you say that the scientific environment is, say, forbiddingly masculine or patriarchal?
The fields that we were looking at were mainly science and engineering, and they are dominated by men. For example, I used to work in CSIRO, and only about 10% of the research staff there was women, not the total people involved in research, but the research scientists. Yet, more women than 10% graduate from universities. So somewhere along the line, women drop out. Now, one of the reasons they drop out, of course, is that they have children and they leave the workforce for a while, and then they find it very difficult to get back into it.
Now, there's also the issue of role models to encourage young women to get into science, but are there lots or are there not lots? Like at a recent forum marking the International Year of the Older Person, that forum recognised the contributions of 25 Australian old women scientists.
Yes, well, there are role models, but unfortunately, eminent women scientists aren't well known to the public. So unless you're in the actual field, people aren't really well aware of eminent women scientists. For example, we all know Gus Nossel's name, yeah, and Robin Batterham and John Stocker and so on, but there are many women in charge of large and prestigious institutes whose names are not known to the public. Mm-hmm. And so young girls at school probably don't know of these women.
But could these women, say, perhaps make themselves more known to the media and everything, and that would start a domino effect of encouragement?
Yes, well, I don't know why they're not better known to the media, but one of the things we did decide at the conference was that women are going to have to get up and get out and do the things and be advocates for themselves, yep, that nobody's going to do it for them. So they mustn't sit back and take the second place that's usually allotted to them.
Okay, and so what do you see happening in the future? Do you sort of see yourself that more women will become involved in science? Are you optimistic of the future?
I think young women do become involved in science. It's when they go into the places of work that they find that they're not in the game. They don't know the rules of the game, and no one will tell them. And this is one of the subjects that you referred to, wanting role models or mentors, so that they can see that it is possible to get on. And with a mentor, that person who's got more experience can tell you how to play the game, as it were, what is expected of you and what is really happening, rather than what is said to be happening.
So are you sort of planning more of these sorts of conferences or a follow-up workshop in the future sometime where these could be more put into action?
We asked the delegates at the conference if they'd like another one, and they all agreed that they would. And we thought in 2 or 3 years' time we'd have another one.
Okay, and was this the first conference of its kind in Australia?
It's not the first conference of its kind, but it's probably the first conference that's been successful in about the last 10 years.
Yep.
Apparently there were quite a few of these sorts of conferences about 10 years ago, and then when they tried to carry them on, there was no interest. And we were quite worried that we would not get enough people at this one, and we budgeted for 100 delegates, but we got over 200 and had to turn people back. So obviously the interest is coming back again.
That was Dr Michelle Smyth. Further information about the conference outcomes can be found on the web at www.vicnet.net/CSIRO-union/ or by phoning Pauline Gallagher in Melbourne on 039206 2288. That's 039206 2288. And tomorrow night at 10:30, ABC TV's Late Line programme will be profiling some of Australia's women in science. Still to come, thought machines and quantum computing.
You're listening to a historical episode of Diffusion Science Radio from November 1999. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com.
This is Discovery, the science show brought to you nationally on ComradeSat. A remarkable new interface between the mind and machine is being developed at the University of Technology, Sydney. The Mindswitch allows machines to respond directly to your thoughts. Ian Woolf began by asking Professor Ashley Craig to explain what the Mindswitch does.
The Mindswitch allows someone to control an electrical device totally with their brain, their mind. They don't need to use hands or feet or anything. So it basically it gives you control over electrical devices with your mind. The Mindswitch technology consists of a band which goes around your head, from which we measure your brain signals. That is connected by a wire, electrical wire, to a little box which sits by your side, which takes the signal and analyses it. Then that has a little RF component or infrared component on it, which then beams off the message to the device, which could be 100 metres away or 10 metres. But that's remote. So that's all it consists of. Or it could consist of a computer. You can activate it through a computer as well. It depends on a number of things. It depends on how you're using the signal from the brain. We can use it proportionally. We can use the one switch, we call it, the one mind switch, to do a number of things. For instance, we've got field trials at the moment with profoundly disabled people. And I'll give you an example of one person with polio who's got to be in an iron lung at night. And this person in our field control, this person was controlling her TV, turning it on, changing channels, changing sound levels with the mind switch, all within seconds.
Wonderful. So do you have companies banging down your door saying, can we sell this to the general public? Because surely everyone will want to be able to throw away the remote and just think at the TV or the computer.
Well, it sounds great, but it's not the case. Australian companies are very difficult to get to commit themselves. We've got people interested and companies interested in investment. The thing is with the Mindswitch, it's still a little bit early to have an actual product on the shelf. And so we haven't had a lot of investors knocking on our door or banging our doors down. But the idea is extremely appealing, and children especially just love the idea and appeals to them, and it's great for science, for instance, just to give science that appeal that it needs. That it can be very fascinating and breaking back or knocking down barriers or frontiers. That's really what we're doing.
But how long does it take to learn to use the Mindswitch?
Well, that's one of the great benefits which distance ourselves from a lot of our co-researchers. I'll give you an example. In Nature, the very prestigious journal early this year, there was a paper published in which 2 profoundly disordered people, disabled people with, I think, with stroke, learned to produce words through their using their EEG or brain signals. It took them, however, 300 hours of training and then 16 hours to produce one paragraph. With the Mindswitch, there's no training necessary whatsoever. It's very simple, very quick. Therein lies its simplicity, but there are problems in terms of complexity with that too. But the wonderful thing, if you're talking about disability applications, there's no training whatsoever. You just have to learn to use the technology, which is a matter of minutes.
So devices like Dr. Stephen Hawking's machine, where he indicates words on a screen and letters on a screen, would that be something you could directly adapt to the Mindswitch?
Oh yes, we could communicate with the Mindswitch, because it's a 0-1 option at the moment, and with more complexity than that, mind you. Yes, that could be the sort of thing we do. At the moment, we've restricted it to turning devices on and off, but it wouldn't take a lot to, for instance, through a notebook computer, to basically pluck out words and put sentences together very quickly.
The general public might prefer to doing that to hunt and peck typing.
Yeah, I think so. I think there's been a great interest out there. For instance, we've been rung up by the Army for applications of the smart soldier, where they're looking basically at communication devices. There are whole lots of applications. The smart house of the future could well have a Mindswitch or a similar device.
Where is your funding coming from?
At the moment, our funding is coming from 2 or 3 sources. The Motor Accident Authority has been a wonderful source of support for our research. In the beginning, when we started this research off, they were one of the few funding groups who had faith in me and gave us that break, other than UTS, of course, University of Technology, which have been great too. They've been giving us a lot of support. But as we got more, as we became better known, we published and in this area, the Australian Research Council has kicked in with some major grants, and so we're not doing too bad at the moment. But So
if you were to make a prediction, how long do you think it would be before you had some product to market, whether it be zapping aliens on a screen instead of a joystick, or products for disabled people, or remote controls of some sort?
Well, we have very soon. We have some of our first products could be looking at being produced next year, early next year. We have been invited by the Olympic Showcase Committee, which is linked to the Olympic Games, which want to showcase innovative and creative Australian technology. We have been invited by them to submit a Mindswitch technology product. So we're hoping to submit that early next year or late this year. But we're hoping, we're hoping to get some products out. For instance, one idea that we've got is, of course, kids love it so much that we thought high schools science departments would love a kit that was educational based and allowed kids or children, they're not children in high school anymore, but allowed the students to basically put together the devices and set up experiments where they're using the Mindswitch. That's one potential device. Another is a great toy, which is Mindswitch based, and everybody wants one when I hear.
As we approach the 21st century, it is not only the interface between man and machine that is changing, but the very nature of the machine itself. We have almost reached the limits of smallness of the transistors our computers rely upon. If we are to have smarter, faster computers, then we need to use an entirely new kind of technology. Quantum computers were first made practical in 1997. It turns out that Douglas Adams was being cleverer than he thought when he had a good strong cup of tea as an integral part of a very smart computer. Physicists at MIT made a simple quantum computer out of liquid caffeine, manipulated by powerful magnetic fields. These computers have the potential to be 100 billion times faster than transistor-based computers. Dr Andrew Djurak is the Assistant Director of the new Quantum Computing Centre at the University of New South Wales. He's working on making a dry quantum computer out of silicon. I began by asking Dr Djurak to explain how quantum computers compute in parallel rather than exploring one path at a time, as transistor computers do.
Quantum computer will be able to take in all those variables and go down every possible path and pick out what the correct solution was, even though there were millions upon millions of possibilities. And the reason for this is that a quantum computer is able to do what's called parallel processing. Now, parallel processing has existed in computing for some time. For example, you can get two Pentium chips and sit them next to each other, and one chip can be doing one problem while the other chip's doing another problem. That means they're calculating in parallel, and they can share out the workload. Now, some of the most powerful supercomputers, like, for example, the type that are being developed at Los Alamos Lab, have thousands of these very fast Pentium chips tied in together, calculating in parallel. Now, the difference between a quantum computer, or at least the quantum computer we're trying to build, and one of these, parallel computers with lots of chips, is that our quantum computer is able to do all of those parallel calculations on just one chip. In fact, it's possible with the individual transistor-like components to be doing a number of calculations at once. Quite a difficult concept to understand, but it's tied into the basic way in which quantum mechanics works. Quantum mechanics being the laws of nature that describe the behaviour of particles right down at the atomic level.
I then asked Dr Djurak about the code-cracking applications of quantum computers.
Cryptography is based upon solving a particular problem, which is breaking up a big number into two smaller numbers, which actually, although it may sound simple, is a very, very difficult problem to do, and it's the difficulty of that problem that means that certain codes are hard to crack. And it would take, for a very large number, even a huge supercomputer, potentially years, to solve that problem. But a quantum computer, because of certain ways in which it does calculations, could do that in seconds.
How fast would a quantum computer go through all these simultaneous calculations and work?
There are some problems which you can show would take the lifetime of the universe to calculate for conventional computers, but on a quantum computer it could do it in seconds. So what we're talking about is not just sort of when you go from like the Pentium to the Pentium 2 chip, where you get, say, a factor of 2 or 3 speed up. We're talking about enormous speed up, something which is impossible on conventional computers. And I'm talking about even if we had the Pentium 2000 chip, right? Even if it was a much, much, much improved version of the current computer chips that are around, they still wouldn't be able to solve the problem because they do calculations in a different way.
So do you think we'll have these sort of things on our desks in 50 years' time, or are they only for special applications?
I think it's very likely that once quantum computers are developed, that they will very likely take over from conventional computers because they will just have so much more power than conventional computers. And I think 50 years' time is a time scale on which there'll be no doubt that quantum computers will have surpassed conventional computers.
I ended by asking Dr Djurak, what about artificial intelligence?
People who have been trying to simulate intelligence using artificial intelligence have run into problems because of the enormous number of possibilities that exist when you try to create what are called neural networks. Because there are many possibilities that thought can take, it makes computing artificial intelligence an incredibly difficult problem. And so people can only simulate very simple thought processes on conventional computers. But you'd see, of course, this is where a quantum computer would have an enormous advantage. And the inherent parallel computing of a quantum processor would allow artificial intelligence problems to be solved much more easily. And it's one of my own personal viewpoints that quantum computers could really have a huge impact in the area of artificial intelligence.
That was Dr Andrew Djurak of the Quantum Computing Centre at the University of New South Wales, speaking to Ian Woolf.
Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com.
That's all we have time for on this edition of Discovery. Contributing to the programme were David Blank, Ian Woolf and Matt Whitfort. Discovery was produced by Ian Woolf in the studios of 2SER in Sydney with technical support from Lucas Koellen.
Sound check by Charles Willock. If you enjoyed the show, you can explore more than 950 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Join my patrons at patreon.com/diffusionradio, make a donation through paypal.me/IanWolf, or listen to Diffusion on your phone or tablet through the Radio Public app.
I'm Carol Oliver. Please join us for more science next week.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.